of alkanes, and we looked at the substitution reactions of alkanes. So this week, I want us to cover alkyl halides. And in this first segment, we're going to cover alkyls and we're going to cover ethers. I hope you do remember what alkyl halides are. So we'll cover alkyl halides and ethers. By the end, I'm roughly going to take around 45 minutes to 30 to 45 minutes to cover ethers and alkyl halides. Then I'll count that done. So the bit about these other segments, we are covering only nomenclature. We might not look at reactions or all the functional groups that you are doing or we are covering in year one, because remember in year one, we cover almost most functional groups and including a few that you didn't cover in high school. So alkyl halides you covered in high school, only that your teachers didn't tell you that you're covering alkyl halides. They are officially called alkyl halides, but you remember something like chloromethane, bromoethane, so 2-fluoropropane, those are alkyl halides. They are officially referred with an organic functional group referred to as alkyl halides. So now those are the functional groups that I want us to cover in this first segment of class. Then when you are done with alkyl halides nomenclature and nomenclature of ethers, then we shall go back now to alkenes. So we shall revisit alkenes, look at alkenes a bit, slightly into it, and then the crown of this particular lecture will be in the reactions of alkenes. That's where I want to spend more time, because I know you've covered alkenes, you've named alkenes in high school. So this is just a repetition and a refresher course into what you guys have already covered. Ethers is another functional group that you've covered in high school, only that your teachers didn't tell you they are ethers. You guys would have run away from school. So now you covered that, and then we shall see when we come to it. Now, in my notes, and I'll send you after class, you'd notice that I have been able to include common nomenclature into the notes. Now, when you read my notes, kindly read the part of common nomenclature to appreciate. But for year one, year two, year three, up until you get to year three of your studies, that is in your third year, that's when you'll be allowed to use common names for some of these organic molecules. But in year one, year two, we strictly maintain IUPAC system of naming. So you can read it. If you feel you will get confused, please skip over. When I'm teaching, I'll skip over teaching you common nomenclature and how we name them. I'll skip it because it's not for you. I'll never ever tell you to give me a common name to a certain molecule, but I will ask you to give me the IUPAC nomenclature to a certain molecule. So now you can skip it over or read just to inform yourself, but understand you need to know the systematic way of naming. That is what you will be asked in these tender years of your university education. So like I said initially, when I started off this course, I said alkyl halides are a group of compounds that are given a general prefix of RX. We said the general prefix of alkyl halide is RX, where X could be either one of those atoms on group 7 or group 17 of your periodic table. I think probably when you continue further with your periodic table, you'd understand why I'm calling group 7. I'm calling it group 7 or group 17. So currently, I know you know it as group 7, but in just a few, maybe semesters, or this is sure what your organic chemistry teacher has for you. It's either you'll tackle it in year 1 or year 2. And then you'll also be told that that group 7 in your periodic table is referred to as group 17, but you can only refer to it as group 17 when you're in campus. In high school, you know it as group 7. high school, you don't know group 17. So now, Rx. So X is either a fluorine molecule, chlorine molecule, bromine, or iodine molecule. Now, alkyl halides can be classified into three. We can classify them either as primary alkyl halides. So primary, I'll use AL to designate in shortcut alkyl halide, or AH, sorry. Alkyl halide. So primary alkyl halide, or we can classify them as secondary alkyl halides. And lastly, we can classify them as tertiary alkyl halides. Now, a primary alkyl halide is an alkyl halide that has been attached to a primary carbon. Now, I do remember a few weeks back when I taught you about primary carbon, secondary carbon, and tertiary carbon. So now, when the X, which is either one of the atoms in our periodic table, group 17 or 7, if we attach that halide onto a primary carbon, then it becomes primary alkyl halide. Now, to jog your memory, let me just draw a carbon for that person who's forgotten, but I believe you should not forget. You've not written your CAT. So we are building into CAT 2 and building into the examination. So now, primary carbon, I remember I drew for you a primary carbon as R, and then we drew carbon with 2 hydrogens. And then we call that a primary carbon. And then we drew a secondary carbon. You drew a secondary carbon as a carbon bearing 2 alkyl groups, meaning 2 R groups. 2 R groups and 1 hydrogen. That was a secondary carbon. And we drew a tertiary carbon as a carbon bearing 3 R groups with no hydrogen. So this was primary carbon, this is secondary carbon, and lastly, that is tertiary carbon. Somebody is saying my writing is not visible to all of you. Most of you, can you be able to see what I'm writing? Collins, you're saying yes. Can you be able to see what I'm writing? Otieno, you're saying no. Collins, you're saying yes. A few are saying yes. If you cannot see what I've written on my board, please refresh your browser. Refresh your browser if you cannot be able to see, because it's a bit visible to some of you. And I said, when you sit in my class, don't sit alone. If your phone was acting like this, it's phone. So now let's move on. If you can't be able to a few, I want to assume that your browser has stalled. So now a primary alkyl carbon bearing 2 hydrogen groups, 1 R group, 1 alkyl group. Secondary carbon, it bears 2 alkyl groups, 1 hydrogen. And lastly, a tertiary carbon bears no hydrogen, but alkyl groups. So whenever you attach your halide, then you attach it there, that becomes primary alkyl halide. If you attach it on a primary carbon, and then if your alkyl halide secondary becomes a secondary alkyl halide. And similarly, if you attach it on a tertiary carbon, it becomes tertiary alkyl halide. So that's the essence of taking you through primary, secondary, and tertiary carbons. And I did talk about the same when I said when you go, we'll also talk about primary alcohol, secondary alcohols, and tertiary alcohol. You know that sometimes these alcohols can differ. And alkyl halides can also differ in the manner that we have been able to portray as on the on the board. Now, let's move on. Now, I will skip the segment that I've told you, common nomenclature. You see this stage where I've written nomenclature and I've got in common names. Now, I will skip common names because I'll never ask you. Let's jump direct to IUPAC system of naming. That's where I want you now to for your cat. I did give you some examples in your cat. Remember, certain as that had fluorine molecules or atoms, sorry, and chlorine atoms. And you remember, I did specifically tell you that when you're quoting fluorine atom, chlorine, bromine, you guys don't have a problem. But fluorine did specifically, it is fluoro. When you're writing, it is fluoro, the U-O. So most of you go for fluoro, F-L-O. No, it is F-L-U-O. We've already named alkenes. In the cat, those were substituted alkenes, they were alkyl halides. You've already done it. You've already covered this topic. Only that somebody just told you those are just substituent on alkenes. But literally, if any alkane or alkene that you're naming the molecule a chlorine atom or bromine atom, that is an halide if you classify it in the broader organic functional groups. So nomenclature of alkyl halides, the IUPAC nomenclature is simple. You just place an O on the halogens that you have. So fluorine, fluoro, chlorine becomes chloro, bromine, bromo, iodine, iodine. I've given you a few examples to act with. I've given you a molecule there, the first molecule there. Now, naming of functional groups. When we talked of the longest continuous carbon chain, it will forever remain like that. Then remember, when you said we can actually see in this molecule, we have a and then have bromide group. So we have a bromo substituent, we have a methyl substituent. Now, if you look at the left going to the right, the methyl will be at position E. But if you start numbering from the right headed to the left, the bromo will be at position number 2. So in rules of naming, we said always name your substituent bar to give your substituent group the lower number possible. So the lower number compared with 3, numbering from the left headed to the right. So when you're numbering this molecule, you will number from the left headed towards headed towards the left. Why? Because the first substituent comes at a lower number, that is position number 2. So, but when you're quoting, you number to give your substituent groups the lower number. But when you quote in alphabetical order. So, bromo comes prior to methyl in alphabetical order. It comes before M. So, when you are quoting, still quote in the same order. So, 2 bromo, 5 methyl, heptane. It is a 7 carbon chain. Now, I believe the rest of them for you now should be a bit easier because we've covered all these molecules. So in your cat, I gave you something closer to this. So when you are looking at it, especially the chlorine, you see where this chlorine in the second molecule, you see where the chlorine is attached? It's attached on carbon number 1. So please don't always be in a rush. Always look at your molecule. Yes, you, especially in the exam. The cat, I can add you a few minutes, but in the exam, it will be strictly 2 hours. You'll not have extra time. And then remember, in the exam, you'll be writing an exam of 70 marks. In the CAT, I give you 1 hour, but you're writing 30 marks. So in the exam, you'll have 2 hours, but you'll be writing for 70 marks. You'll be trying to claim all your 70 marks. So yes, no time essence, but when you're in an exam, compose yourself and check. Most of the time, students never see that chlorine atom. Chlorine just is a C with an, and if it is put at the end of the chain, like I've put it at the chain, some students will not see that. That will be what I will be gauging. So you don't see that your name does not begin with 1 chloro, you fail, not even looking, because remember, it is IUPAC system or naming. You here in Kenya, in Kibabi University, will give the same name as my student in Embu University. You'll give the same name as my student in Kirinyaga University. If I was giving you the same exam, you'll give the same name with a student in China, with a student in Britain. So now, if the name does not start with 1 chloro for that particular molecule, I'll not even look at it. That's why I did say marking a wrong answer is quite easy than marking a correct answer. If I see 1 chloro, I'll read, did you get the others correct? So it will take me time. But if I don't see 1 chloro, you failed. So the rules of nomenclature for these guys are the same, because it is more or less merely repeating what we had done prior to it is just merely we are repeating what we had done prior in our previous classes. Now, we covered cycloalkanes. For cycloalkanes, I said when you have these 2 groups, when there are only 2 groups, you get one that is alphabetical. If you're only having 2 groups, this is an ether, an E. So this is an E. And then this other one is iodo. E comes I in alphabetical order. So it gives, it tells you that the E, where the functional or the substrate is attached, where the E is, that gets position number 1, only when you have 2 substrate. If you've forgotten, go back to rules of naming. We did that, I think it should be 3 weeks ago. So mind yourself. Now, whenever you're naming more than 3 functional, 3 substrate in a cyclic alkane, then you name it in a manner, you pick position 1. And the one that becomes, when you number, you don't number them biased the way you number that are 2. So when there are 3 and above, more than 2 and above, you will number such that the one that takes position number 1, the second substrate will have a lower number, consequently the third and the fourth. So now when you're numbering this molecule here, goes without saying that either the methyl or the chloro is at position number 1. And if you had what I said 3 weeks ago, then you know automatically methyl is at position number 1. Why? Because if you pick chlorine, then it makes methyl number 2, bromine will be at a higher number possible. So without say that methyl will be 1 and the chloro substrate will be at carbon number 2. So the bromo is at carbon number 4. So if you went through my notes 3 weeks ago, I think numbering cyclic alkanes will be an issue. Number 2, when you're naming cyclic alkanes, don't forget the prefix cyclo. Don't forget it. So that is the second pitfall. The first pitfall I will be testing is, do you remember how to number? If you get the numbering correct, fine. The next thing I'll be testing is, will you remember it is cyclo low. You remember, then you are okay. If you're with me till that point, please type a 1 for me as we continue. I just want a couple of ones, some 2, 3 ones, and then we can move on to the next order of business, and that is ethers. Okay, I've seen a 1 from Wafula, from Obare, Philemon. Those are enough. Now let's move on. Stop typing. Those are enough. Let's move on. Now, ethers, my next order of business. Pardon me. Let me just see if this phone call is an important phone call. Hello? Yes. I am in class. Which issue do you have? Can it wait after I finish my class? In the same class you are. What is your issue? I haven't logged in, that you have been logged out. The number is a bit high. You can't log in an hour into the class. Once we begin, you only get 15 minutes to. Once you don't log in around that time, you're out of my class. So timing is important. Find somebody and share. Now, first years, let me tell you, when you're logging in into my class, you only have the first 15 minutes. In a big class like the big class you are, right? Like right now, I'm having, not all of you are in class. I want to assume some of you are sharing, but you are 271 right now in class, and it is playing around there. Once you come in that many, the system will automatically lock you. It will lock you out. So a few of you will be allowed to come in. So like I said, when you log in, you knew we have class at 11. I give you 15 minutes to log in. Then I log in and start. Once I start teaching, the system might not allow you in quite easily. So know that next time, log in. You log in before I in. Once I log in, it will lock you out. So don't start calling me like your fellow student here. Now, let's move on. Let's move on to ethers. So now for ethers, we've already said that the general abbreviation for ethers is ROR. So now I said it was R, and I hope you remember your general abbreviations because they are important. I hope you remember the general abbreviation. So I'm saying for ethers, we have ROR. Very important. Now, if you remember that, then we can have, since we have an ether with 2 alkyl groups, those 2 alkyl groups could be the same. So for example, I have a methyl CH3, and then my 3 is misbehaving, oxygen, and then CH3. I can have that. So now these 2 R groups, methyls at both ends, they are the same. That is what we refer to as a systematic ether, when the 2 R groups are the same. But sometimes we can have the R groups differing. So for example, I have CH3 and then oxygen, then C2H5, or CH2, CH3. So I have one R group is a methyl, the other is an ethyl group, then that is what we refer to as an unsystematic ether. So we have systematic ether, both R's are the same, and systematic ether, the R's are different. So that's why you can see on my board an R and an R prime. this is R prime. Meaning, whenever you see R prime, those two R's are different, or I can say R1 and R2. We have two different alkyl groups. Now, that is the much that I think the farthest that I can go in reminding you what ethers are. So we can either have identical alkyl groups or we can have different alkyl groups. Now, nomenclature of ethers, equally, I will skip the nomenclature of ethers, but you'll find it, you'll get used to it when you go to the labs. You'll find me talk of diethyl ether. Those are common names of ethers. Now, for your class, all you need to know is the systematic nomenclature of ethers. How do we name ethers in the appropriate IUPAC name? So now, when we name ethers, basically what we do is you replace, you look at the alkane name. Name of your alkane, you replace the YL. You notice when you go methyl, propyl, butyl, a pentyl, cyclobutyl. I taught you cyclopropyl. We covered those cycloalkane as a substituent in your CAT. If you remember in your CAT, we covered cyclopyl. In your notes, you have cyclobutyl when you're covering alkanes. Now, you are replacing that Y of your alkyl group with OXY. I'll repeat that. You are replacing, let me get a cleaner blackboard. So you are replacing the YL, where is my pen? You are replacing the YL of your alkyl substituent or R group with OXY. You are replacing it with OXY. So methyl, from a methyl group, remember a methyl was just CH3. You are replacing it with OXY, so it becomes methoxy. Ethyl becomes ethoxy. Propyl becomes propoxy, and so on and so forth. So now, if we have other complex alkyl groups, like for example, you'll see on your notes, because we can have other groups. If you look at my notes nomenclature, I did talk about an isopropyl group. And an isopropyl group is just a rearranged mode of writing. So isopropyl was something like this. If you don't remember, let me draw it for you. So isopropyl, you had something like this, CH3, and then you had C, and that C had was attached to, so it is a CH with a bond hanging. That CH is attached to a methyl down here. This functional group was what, or this substituent, when you get such a substituent attached to a bigger molecule, then you call this isopropyl if it is a substituent, So now, instead of isopropyl, now when you are dealing with what do you call them? We call them ethers. So when you're dealing with an ether, there will be an oxygen attached. So methyl will be CH3O, so that it reads methoxy. So now this isopropyl, it will be isopropyl with an oxygen attached there. It's just a bond hanging. To be an ether. And then ethoxy will be, ethyl is CH3CH2. That is an ethyl group. But ethoxy will have a oxygen. For it to be ethoxy, it will have an oxygen. Pardon me, just a moment. Doc, how are you? I'm fine, thank you. I'm in class. Can I get you at around 2? Okay, thank you. So now, ethyl, for when you're transiting from alkyls to alkoxy, and those are ethers, you add an oxygen. So methyl is CH3O, that is methoxy. Ethyl, the way you know it as CH3CH2, you add an oxygen. Whenever you see that oxygen, that is no longer an ethyl, it's now an ethoxy. It is an ester, and so on and so forth. Now, you look at the notes and then you will see quite a few additional molecules that I've put there for you. So I've given you an example of isopropyl. Now it is isopropoxy. Isobutyl for the alkyl R, when you add an oxygen, it becomes isobutoxy. Tatbutyl becomes tatbutoxy when it is an ether. So that is how you name or you classify such kind of compounds. Now, another thing, I want to give an example of an ether, so that we can actually name that ether using the new acquired system of naming that we are talking of: methoxy, ethoxy, isopropoxy, sec-butoxy, tat-butoxy. So let me show you an example of such. Yes, there we go. Here we go. So look at this molecule here. If you look at this molecule, it is an ether. And if you want to know it is an ether, please look at this long continuous chain. It will give us our parent name. That is an R group and is attached to an oxygen. Then this other chain here, that methyl, is an R group. All of them are joined with, are connected with an oxygen in between. So R, that is an ether. If you look at this other group also, this is an R group. And then there is an oxygen, then there is an R group, R-O-R, ether. So whenever you want to name an ether, I haven't given you rules in naming ethers. I'm going to give you just now by speaking. So whenever you name an ether, please look at your molecule and identify the longest continuous carbon chain. That's what's going to give you the parent name of your ether. And then identify the shorter chain after the oxygen. So identify where the two R's are. The longest continuous R chain will give you your parent name. Then the smaller R chain is the one that's going to give you a substituent. So now, what am I saying? Let's do it in practice so that I'm not only speaking. Let me pick color red. Now, if you notice, this is the longest continuous carbon chain. And if that is the longest continuous carbon chain, it is what is going to give us our parent name. So we write. Now, how do we number? When we number from the left headed to the right, we notice that our substituent is at carbon number 2. When you number from the right headed to the left, the substituent is at position number 3. So the correct numbering is the left going to the right. So carbon number 1, carbon number 2, carbon number 3, and carbon number 4. Number 1, number 2, number 3, and number 4. So now, the attached substituent is at carbon number 2. That substituent is bearing 1 carbon and an oxygen. So that tells you that this molecule, it is a methyl group with an oxygen. So that substituent becomes a methoxy. So the name of the whole molecule becomes, where is the methoxy attached? At carbon number 2. So the name becomes 2-methoxybutane. You see how easy it is to name. Now, let's look at molecule number 2. Molecule number 2, I've tried to complex it a bit. So already, look at, I said first thing, identify your longest R. Longest R is this R here. That's the longest chain. Shortest chain is there after the oxygen. Are you seeing a shorter chain here? After the oxygen, are you seeing a shorter chain? So that becomes now your substituent. So now, number your longest chain. Now, already if we've said this shorter chain becomes your substituent together with the oxygen, it becomes your substituent. Then it goes without saying that you will number from the right headed to the left, because it will give our first substituent at carbon number 1. So you number the chain, that is carbon number 1. This is carbon number 2, that is carbon number 3, that is 4, carbon number 4, and lastly we have carbon number 5. Good. Now, another thing. So we know already that this smaller chain with the oxygen becomes our substituent, and it is at position number 1. So we know we have an ethoxy, a 1-ethoxy. Then, if you look at the molecule, we have a methyl. Where is the methyl? At carbon number 3, according to our correct numbering. So now, when you quote, you still quote alpha. E comes before M. So the molecule becomes 1-ethoxy, 3-methyl pentane, because it's a 5-chain carbon. I believe I was keeping quiet so that it sinks in. 1-ethoxy, you quote alphabetically. So we have 1-ethoxy, 3-methyl pentane. Now, when you're quoting your names, for the CAT, I was a bit lenient. For the exam, I will not be lenient. Remember, between letters and numbers, you have hyphen. Between numbers and numbers, you have commas. Do not just write 1-methoxy without the hyphen. So also know your content. So in the exam, I'll not be lenient. Why? Because I've reminded you. Now let's go on to the third example. The third example there, I have given you an example where we have the substituent as isopropyl. Are you seeing where now I drew for you the isopropoxy? In the notes I gave you isopropyl, sec-butyl. You need to know how they look like, because this group here, the whole as it is, this is an isopropyl group. With the oxygen, it becomes isopropoxy. So now you already need to identify. So you identify that this is a substituent with the oxygen, that is a substituent with the oxygen. So longest continuous carbon chain is in the middle. Once you notice that it is in the middle, then you go ahead and number them and see what is your longest continuous carbon chain. How many carbons does it bear? We can number from the left or we can number from the right, because we have isopropoxy on both sides. So either numbering will be okay. That one who starts from the left, that one starts from the right, you'll end up at the same name. So now carbon number 1, I'll start mine from the left. Carbon number 1, carbon number 2, carbon number 3, and carbon number 4. So the longest continuous carbon chain has 4 carbons, meaning you're talking of a butane molecule. And then, like I've said, those R groups, they are isopropoxy group. Where do you have them positioned? You have them positioned at carbon number 1 and at carbon number 4. Then you go quote your name as 1, 4 hyphen. They are two isopropoxys. Don't forget the word di, because you can't say 1, 4. 1, 4, those are two numbers. Then the prefix that comes after the two numbers is di. If you had quoted 3 positions, then the prefix that comes is tri. You quote 4 positions, the prefix that comes is tetra. So 1, 4 di isopropoxy butane. So molecule looks complicated. It is not complicated. Once you know, then we move on. So if you're with me up until that point, I'm done with this first segment of the lecture. If you're with me up until this point, please type a 2 as we move on. Type a 2, then we can continue to the next segment of our lecture, and that is the alkene handout. Okay, I'm seeing several truths: Brian, Deborah, Timothy, Paul, Pauline, Benson, Philemon. Those are enough twos. Let's continue. I want to believe that the point is home. The point is home. Then let's continue. Now, if you have a question, please feel free to ask, or you can ask at the end of the lecture. But if you have a question on this particular small topic, please ask these two subtopics. Ask, and then we continue to the next segment of our lecture. Any question? I don't think, Gen Z, I don't think you telling me to pardon is a question. Pardoning is not a question. I can assume you and I move on. I've said if you have a question, ask. When you tell me to pardon, I've been teaching for the past almost 35 minutes. Now, when you tell me to pardon, do you want me to repeat the whole 35 minutes? I'm sorry, I can't do that. I really don't have the time for that. So I've said if you have a question, ask. Now, somebody called Otieno Jackson, you're asking me, what does ISO mean? Jackson, have you been in my class? Are you in my class? Are you seeing the notes in my class? What is this? You're asking me what is ISO. Are you seeing it there? I already taught you these functional groups in your alkane handout. It is there. Methyl, ethyl, propyl, sec, butyl, isopropyl, isosec butyl, tat butyl. I already taught you those functional groups. So when somebody asks me what is iso, how am I supposed to answer that? That in itself is not even a question. That's a very crooked question. It's not a question, because I don't know how I'm supposed to answer that. Harriet, you're saying, Madam, where does the ISO? A lot of you are asking me very weird questions that do not have legs. Where is the ISO term coming from? And why are we naming it as isopropyl? Please, clarification. It is there in the notes. Are you seeing this functional group? Hey, Jamil. Eh? Sometimes I need to teach you and I don't need to spoon feed you. I need to teach you and I want you to be teachable. So when I was mentioning the ISO, why when these questions not coming in? I've said when you have a functional group, stop typing, those silly of you who are typing things and I'm explaining things. You can't type and I'm explaining things. Stop typing. When I'm explaining something, please be attentive so that we do not repeat some mistakes. Now, assuming we are not dealing with ethers, assuming I'm not dealing with ethers, I've said, when you have groups, for example, when you have a CH3 group, CH3, we are talking about attachments, we are talking about substituent. CH3 is a group coming from methane, whereby you've just removed one hydrogen of methane so that they are substituent, because when you attach, you'll attach a CH3 group somewhere on your long continuous carbon chain. Or for example, when you're talking of this cyclopentane, when we attach, we don't attach as a methane molecule. You attach it as an alkyl group. An alkyl group is a carbon having one hydrogen less than the usual alkane. So that's why I said methane give you methyl. Methane is CH4. When you remove one hydrogen, you get CH3. That is alkyl group. So it will be an alkyl group. That is your methyl. It will attach anywhere on your molecule. So now, if we are not attaching a methane molecule, we are attaching it as an ether. All we will need to do is add oxygen, then put our CH3. This now changes from an cycloalkane, it becomes an ether, this molecule. Why? Because we've added that oxygen. So when you're looking at those functional groups that I've given you there with their names, because the names are just portrayed. They're on the handout. I'm not reading something from mass. It is there in the handout. I've given it to you, I've drawn it for you, and I've labeled it for you. Why? Because I knew questions are going to come. So I don't want silly questions. I've labeled it for you. Now, revisit your alkane notes. It tells me that, you see, you are in advanced organic chemistry. You're not covering the organic chemistry you covered in high school. We are at advanced level. And at advanced level, we deal with some funny organic structures. And these funny organic structures, the ones that I want you now to know and internalize. The ones that you know, methyl, I'm not interested in methyl. Ethyl, I'm not interested in that. You already knew. You already know, your teacher in high school taught. So I'm teaching you the bit where your teacher did not teach you. The advanced now level. We mix the advanced level with the ordinary level that you knew to make you an advanced chemistry student. Now, at this level, I am saying, whenever you are seeing CH3, that is an alkyl group, you already know that is a methyl group. CH2, CH3 up with an open bond, that is ethyl, butyl, pentyl, and so on and so forth. Those ones you know. Now, the bits that you do not know is the isopropyl, sec-butyl, tat-butyl. Cram those structures. You begin with cramming them, and then you practice until you know them. So for now, I know you will cram. When I was yourself in year one, we crammed these structures until you know it. You cram and practice until you know it. So whenever you see an attachment, so the other attachments you can easily tell, the ethyl, propyl, butyl, pentyl, cyclobutyl, those ones you know. But now the challenging bit is now these three: number one, number two, number three. Those are the challenging ones. And I began with isopropyl. And I drew that isopropyl. So for those of you who are asking me questions, I think I drew that isopropyl here. I said, whenever you're having an attachment, and that attachment is going to be CH3CH, and then that CH has a methyl group written in the way that I've drawn it. You can't draw it in a different way. If I change the orientation of my group here, it stops being isopropyl. Tuko pamoja. I cannot draw this molecule and say CH3, CH, oxygen, CH2. Sorry. I changed that CH3 where it is and I put it here. If I change the orientation of that, this molecule is not isopropyl. Look at what I've written. CH3, CHO, CH3. This molecule now becomes a different ether. It becomes, look at it. So when I'm saying, please bear in mind, this molecule becomes, and in fact, if I write it like that, I think this H, let me see how many, the carbon is tetravalent. We need to have 4 bonds around carbon. So this particular carbon, let me see how many bonds does it have. It has 3. So there is a 2 that is missing there. There is a 2 that is missing here. So now, if I draw that molecule, I've just changed the way the molecule looks. Then this molecule is no longer isopropyl. It becomes a methoxyethane molecule. So now, please, when I'm talking of isopropyl, an isopropyl group is CH, where is my pen? CH3. And then that CH3 is attached to carbon with the hydrogen and a bond hanging. And that carbon with the hydrogen is bearing another methyl group, CH3. So this CH of yours is bearing 2 methyls. And the bond is hanging. This functional group is what you call isopropyl. Pamoja. Leave around the oxygens. Now, I'll come to the oxygen. Now, sec-butyl. Sec-butyl is written as CH3. This one you will cram. I have no way of making it easier for you. You cram until you know it. Then once you know, you know. So CH3 and then CH2. And then, sorry, the 2 is not visible well. 2, like that. Then it's attached to a CH with a bond hanging, and that CH bears a methyl group, CH3. Whenever you see this kind of orientation, this functional group, this alkyl group, it is an alkyl group, is now referred to as sec-butyl. Sec-butyl. If you're asking a question and you're not drawing this and you're not writing, then you're not serious. Now, tert-butyl. Tert-butyl. Sec-butyl from the word secondary butyl. Tert-butyl, the tert means tertiary. So, but you don't call it in full. Just write sec-butyl, tert-butyl. I will understand what you mean. So now, tert-butyl is a molecule. I'll draw it in black because my board is almost full. So I'll draw it in black somewhere at the corner here. So tert-butyl is a CH3 group attached to a C. That C is having a bond hanging, and that C is attached to another methyl group, and it's attached to a third methyl group. This kind of arrangement is an alkyl group referred to as tert-butyl, or what I'm calling tertiary butyl, but you don't call the whole name, you just call it tert-butyl. Sawa. And I'm saying the word tert comes from tertiary. The word sec comes from secondary. So isopropyl, the number 1, this one here. Number 2, sec-butyl. Number 3, tert-butyl. Those are the 3 complex alkyl groups that you were never taught in high school. You'll never find this in high school. But now you are finding it in our advanced organic chemistry. I'm hoping I'm together with everyone. Somebody is still telling me they cannot see. And like I said, if you cannot see, reboot or refresh your browser. Number 2, find a friend. So stop writing for me, it's not visible. I cannot do anything. Visible on my end, it is visible to quite a few people. I cannot help you. Now, if you have that, those are alkyl groups. You notice that those carbons, look at that carbon of isopropyl. It is having a bond hanging. If you count number of atoms around it, there are 3. So it is an alkyl group because you'll attach it somewhere. So whenever you see a compound having such an attachment, a functional group having such an attachment, that's when now you will name this that isopropyl, because it will be hard to name this molecule and we number it. We can't number it. We can't. So whenever you see this kind of attachment on a molecule, you remember alkyl groups, isopropyl. Whenever you see this kind of arrangement and attachment, and it is a substituent, if it is a substituent, there will be substituents because these are R groups. So if it is a substituent on a molecule somewhere, the substituent is called sec-butyl, and that is called tert-butyl. Now let's go back to what we are discussing. We were discussing ethers, and I said an ether, you will add an oxygen to your alkyl group. So we will add an oxygen. I will add an oxygen here. If I add an oxygen to that isopropyl, it changes, the name moves, you remove the isopropyl YL of your alkyl. You remove it, add OXY. So the name becomes isopropoxy. When you add an oxygen to your isobutyl, it changes from isobutyl to isobutoxy. You remove the YL, add OXY because of that oxygen. And then same thing to your butoxy, I'll add my oxygen in red. If I add an oxygen there and I attach it as a substituent somewhere, that substituent is now going to be referred to as tert-butoxy. Am I with everybody right now? Those who did not understand, can you now understand? Now, Harriet says, okay, good, you've understood. Now, thank you. Now, I think somebody asked the question, a few of you have benefited out of it. So now I hope I'm at par with you. Good, now let's move on. Now, once we know that, so naming ethers becomes easy. So the first thing that you have, you identify your longest continuous R, that's your parent. Then the shorter R together with that oxygen, it is now substituent. So you've named ethers in high school. I think there was a point where you named ethers in high school. Most of the time they used to like methoxy and ethoxy. But I'm not sure if your curriculum still carries the same. Talking of my curriculum back in the day and when I was teaching. Right now, unless I inquire, I can't really remember how much you've done. So good. So I think the point is home. So those isopropoxy, sec-butoxy, tert-butoxy, you will cram their structures for now. After a while, after a period of time, you will get to understand them. There is no shortcut to it. So now, if we now go back to naming, to the structure that I gave you, so I believe now you understand why I was saying that when you ask me where the ISO is coming from, the question is redundant. It's a stupid question. Now you understand why I was saying it's a stupid question. Because already the whole group is called an isopropyl. So when you ask me where the word iso is coming from, you see why I'm saying that the question is it's weird. Now I think you understand that. Now I want us to move to our second bit of the lecture, and that is alkenes. So I want us to discuss alkenes. Let me just pull up the notes. Okay, good. Here we go. So now in that alkene handout, The first thing you'll encounter is just a few questions to jog your memory here and there, but that is not for me, that is for you. Now, let's discuss alkenes. Already, we know what an alkene is, but I don't want to assume you know. Alkenes are compounds that we know the general formula for alkenes, CnH2n. But you remember, we don't deal with molecular formulas here. We actually deal with general formula and the general abbreviation. And I did say when I was introducing that the abbreviation for an alkene molecule is this. This was the general abbreviation for an alkene, like that. You just draw carbon with the double bond carbon and with the 4 bonds hanging. That is the general abbreviation. And that's what we shall stick on. Now, I've given you a few alkenes there. I've given you an alkane with the molecular formula, an alkene with the molecular formula. But do you remember the molecular formula that we wrote for cycloalkanes? Cycloalkanes had a molecular formula similar to an alkene. That's why we are not measuring our discussion on the molecular formulas, because cycloalkane had a similar molecular formula as an alkene. And then when you look, we go ahead and cover, when I'm finishing, they're what called cycloalkenes. Cycloalkenes, I've given you an example there. That is a cyclopentene molecule. So a cyclopentene molecule will have a molecular formula like an alkyne, because if you go back to your organic chemistry, that molecular formula CnH2n minus 2, that was the molecular formula for alkynes. Now, when you are talking of cycloalkenes, they will have a similar molecular formula with alkynes. So we are painting it forward. Now, with that in mind, then we can be able to say that whenever you're given a general formula, for example, for C8H14, when you talk of C8H14, you can first of all think in your head. If you're given that molecular formula and you're told to draw the molecules, the isomers containing C8H14, you can draw 4 different types of molecules. So you'll first of all think, okay, C8H14, now what are you having? That's a general formula to what? So first of all, you'll think, if that is 8 and that is 14, then I might be talking of 1, a double bond. 2, I might be talking of either, if not a double bond, and 2 double bonds for that matter. Because if it was only 1 double bond, then I would have had C8H16, right? If that was just a single alkene, the molecular formula would have been C8H16. When I talk of C8H16, you can think of drawing a molecule that has a double bond somewhere, an alkene with a double bond somewhere. Or you can draw a ring, an 8 carbon chain ring cyclic alkane with 8 carbons. It will give you the molecular formula C8H16. But now I'm saying in my notes, I've challenged you, and I'm saying I want you to think about a molecule containing C8H14. If you think of C8H14, what tells you? What is it? Because it's not fitting in the molecular formulas that you know. But now think like a scientist. If there are 2 hydrogens less than 16, then it means that molecule has 2 double bonds, right? That's the only time you can lose 4 hydrogens. So it has 2 double bonds. So the molecule has 2 double bonds. If you draw a chain, an 8 carbon chain with 2 double bonds wherever in that molecule, you will get your C8H14. And then a different route that you can use is you can draw a ring molecule. And like I said, a ring molecule will mimic a cycloalkene will have lost the 4 hydrogens. So somebody tells me, Brian or Luco, you'll draw a cyclooctene. Very good. So you draw rings. Or you can still have a complete ring, not an alkane ring and a double bond somewhere. An alkene ring with a chain having a double bond somewhere. And then another option is that we can have 2 rings. We can have 2 rings joined together. So say a 4 carbon chain with another 4 carbon ring and another 4 carbon ring joined together. You will be able to get that kind of molecular formula that you have. Or we can have a triple bond. So what am I saying? What am I saying? I'm saying, in short, that whenever we write, whenever we have molecular formula, that molecular formula can give you so many different isomers. So all these molecules, when you draw, including your cyclooctane molecule, when you draw them, it should be cyclooctene. When you draw them, those molecules are isomers of each other. Now, that's the point that I wanted to bring home. So that with that in mind, that we have those molecules, or I can give you a molecular formula and ask you to draw the isomers within. Now, those isomers that come out of it, they are what we call structural isomers, meaning they differ in their structure component. So like I've given you a few examples there. I've talked of, let me pull this. I've talked of, you can have a double bond, a molecule. You can draw this molecule having 2 double bonds within the ring. You can draw a ring and a double bond. You can draw 2 rings, and you can draw a triple bond. All of them will constitute C8H14, that molecular formula that we are having. So sometimes when I target a question, I will target a question that's direct. Otherwise, when you deal with molecular formulas, like now you are understanding, we can have so many isomers attached to it. Now, let me move to where I've given you these structural isomers so that you see. Now, this is the first example I've given you. 2 double bonds within that molecule, or a triple bond. You can see the triple bond will still account for that molecular formula. And we can have an octene. So like I said, Weta was talking of octane. No, it is not octane. We are in alkenes. And remember, it was C8H14. That is a molecular formula. If you count that and I go to what you already know, that's molecular formula of an alkyne. Because C8 for alkenes, it should have been C8H16. So this is an alkyne. But besides an alkyne, I'm telling you, it does not only fit an alkyne profile. It can fit a double alkene profile. It can fit an alkyne profile. It can fit a cyclic alkene profile. And it can fit 2 rings joined together. If you count those carbons are 8. We have carbon number 1, carbon number 2, number 3, number 4. Carbon number 5, number 6, number 7, and oh sorry, I skipped one, number 8 down here. Those are 8 carbon atoms joined together. So now I hope the point is home. whenever you have a molecular formula and how you are taught molecular formula for alkanes, alkenes, alkynes, they don't only conclude or necessitate, they don't only and specifically an alkyne molecular formula does not only fit an alkyne. Right now we've said it can fit an alkyne, it can fit a double alkene, two alkenes, and then it can fit a cycloalkene, and it can fit a cycloalkane where you have two rings joined together. So now, if the point is home, then we can now proceed. Now, unsaturated hydrocarbons, because remember we are dealing with hydrocarbons. So already we know alkenes are unsaturated. We have three classes of unsaturated hydrocarbons. There are three. One is alkenes, number two, alkynes, number three, aromatic compounds. Those are the three unsaturated hydrocarbons that you will constantly meet by the time you finish your 4th year organic chemistry course. So there are three unsaturated hydrocarbons. I've said alkenes, alkynes, and aromatic. Aromatic is new to you. I'll give you the spelling, aromatic. Aromatic compounds. Aromatic compounds. They are unsaturated. In 3rd year, I'll tell you what aromatic compounds is. But if you've ever gone to the lab and heard of a solvent you call benzene, benzene is an aromatic compound. Actually, aromatic compounds rotate around the chemistry of benzene. It is the one that is that brings about the whole study, organic chemistry study of, we are just studying benzene and its compounds. So it is one of the aromatic compounds. A benzene molecule looks like this, so that you don't wonder, hey, where is the unsaturation coming from? That is a benzene molecule. It is a cyclohexane with 3 different unsaturations. So that is now benzene. If we remove those double bonds, those 3, you can see it has 3 double bonds. If you remove them, that's not benzene. So benzene has those 3 double bonds there. So that's why I'm saying aromatic compounds are classified also under unsaturated hydrocarbons, alkenes, alkynes, and aromatic compounds. Now, moving on. Nomenclature of alkenes. Nomenclature of alkenes. This bit I know, you know, so we'll not look at common nomenclature. That's not important. We'll directly go to IUPAC nomenclature. You already know. So I'm not going to spend some time. I'm just going to highlight maybe a few things if you've forgotten. When you are naming alkenes, you remember longest continuous carbon chain will give you your functional, containing the functional group. It should contain the double bond. So when you're naming your longest continuous carbon chain, that carbon chain has to have that double bond for it to be classified as an alkene. But also, when you number to give your alkene a lower number. So for example, look at the butene molecule in this, the first molecule. You see, I numbered from the right. Why? Because it gives my double bond position number 1. So remember, when you're quoting the position of your double bond, you quote that position where the double bond is starting, not where it's ending, where it is starting. So some of you quote where it is ending, like I can't call this 2-butene. You quote where it's starting. It's starting from carbon 1. That's where you're starting numbering from. So carbon 1, so that molecule becomes 1-butene, or but1-ene, also accepted. Look at the second molecule. We still have a butene molecule, but we've changed the position of the double bond. We put the double bond between carbon 2 and carbon 3. Here, for this molecule, we can number from either side. It will give us the same name. But when we quote where the double bond is starting. It started at carbon 2. It is between 2 and 3, so you quote 2. It is 2-butene or but-2-ene. Separate the suffix that is the in, the prefix, and then put 2 in between and put hyphens on both sides. But-2-ene. Very much accepted. That much I know you know. Now, number 3 is very simple. I want to come here. Look at molecule number 4. So when you are numbering this molecule, I know I put this one here because some of you will take this as the longest continuous carbon chain. But where is your double bond? Your double bond is down here. Your double bond has to be part of it. So now longest continuous carbon chain becomes that direction. Move from down to the left. It is a 6-carbon chain. At position number 2, we have a 3-carbon substituent. That becomes a propyl group. And then the alkene is at position number 1. So the molecule is quoted as 2-propyl, 1-hexene, or 2-hexane. Now, when you're writing the names, please, first years, just write one name. You don't need to write for me 2 names. If you write for me 2 names and one is wrong, I will not know which one you want me to mark. So when you're giving names to your molecules, just give me one correct name and leave it there. Don't write 2 names for this. Are you seeing me writing? The other accepted IUPAC name is 2-propyl hexane. Are you seeing me writing there? I haven't. So it is accepted. You already know it's accepted. So when you're writing, you either give it as 1-hexene or hexane. Pick one. And stop wasting your time writing me 2 names. It's only 1 mark. I'll only give you 1 mark. So save your time. Now, that was rule number 1. Let's go to the second rule. Now, when you're naming, you cite your alpha when you're numbering, not naming. When you're numbering, and then you've numbered, you have your substituent. Now, remember, the substituents will be quoted before the name. The substituent comes before the parent name. I believe that much you know. So now, that is rule number 3. Rule number 4. You already know these things. When you've cited and the substituent have been cited, when you're citing them, you've numbered correctly. Now, when you cite, always cite alphabetically. Always cite alphabetically. So bromo and chloro, bromo comes before chloro. So you cite bromo, then you cite chloro. It doesn't matter their positions. I believe that much you are well acquainted with. Now, another thing that that number 4 is saying, I think, if the same name of the alkene functional group, point number 4 tells us that if we have a similar if the double bond will be at the same position. So say this is carbon 1, 2, 3, and 4. If we number from the left, it becomes from the right, carbon 1, 2, 3, and 4. So now, if you have a situation where somebody is saying that you cannot hear me, my microphone is vibrating. If you cannot hear me, your browser has stalled. Can you all hear me? Am I audible? Dorcas, they cannot hear me. Am I audible? I can see yes. I believe I should be, because when my microphone is vibrating, thank you. So Dorcas's phone has stalled. She needs to reboot it. Refresh your browsers. So now, okay, good. Let's continue. Now, whenever you have a scenario like this, if we on the left, our double bond is at position number 4. If we number from the right, our double bond is at position number 4. Then you number from the side that gives you your substituent a lower number. So now look at this numbering. If we number from, look at this, let me just number so that it is well understood. Number 1, number 2, number 3, number 4, number 5, number 6, number 7, number 8. And then let's number from the other direction. Number 1, number 2, number 3, number 4, number 5, number 6, number 7, number 8. So both sides give us our double bond at position number 4. Very good. But one side is correct, the other side is wrong. Why? You will then pick the side which give you a lower number on your substituent. So if we number from the left, from the left heading to the right, our substituent is at position number 4. Our other substituent is at position number 7. But if we number from the right heading to the left, our substituent is at position number 2. The other one is at position number 5. So 4 and 5 are lower numbers compared to 4 and 7. So you're going to pick the second numbering from the right heading towards the left. So that's why I gave you those two names there. I have rule number 5. Now, whenever we are naming cyclic alkanes, we don't need the position. Why? Because it's always taken that the double bond will be carbon 1 and 2. Because we said we number to give our alkene the lower number possible. So whenever we are having cyclic alkanes, no need of saying one cyclo, because it is always taken that the double bond will be at carbon 1 and 2. So for it to be 1 and 2, you will then proceed to give other substituents a lower number. So it means if we have a substituent here, our number 1 is here, number 2, so that the substituent is at position number 3. If we number the other way around, our substituent will be at a higher number, and we've already said you should number to give your substituent lower number consequent after the double bond. So if we number 1, sorry, where is my pen? 1, 2, 3, 4, 5. Position 5 is higher than position 3. So that's the wrong numbering. So always know that for cyclic alkenes, the double bond is at position 1 and 2. Then you will proceed your numbering to give other substituents a lower number possible. Sawa sawa. Okay, so now let's continue. I believe the other examples are there, and you can be able to see or practice on how I was able to do the numbering. The last one I did not do the numbering for you because I wanted you to figure it out. Always know that the double bond is at carbon 1 and 2. Then you can proceed to envision the other positions. Now, I want to teach you what we call vinylic carbons and allylic carbons. You remember when we talked about hybridization? So I said whenever you have a molecule, I can always give you a molecule, and that molecule, I can always ask you the hybridization of the carbons within the different molecules that I've given you. Now, so whenever you have a molecule like this, whenever we have molecules like this, like these particular molecules. If you look at these molecules, these carbons, let me change them to black. These black carbons in the middle, the carbons bearing the double bond. I'm redrawing them in black, so that I can call black carbons and carbons that I've drawn in red. So these carbons in the middle here, I've drawn them in black. These carbons in the middle here, I've drawn them in black. They are what we call vinylic carbons. They are what we call vinylic carbons. Basically, they are the alkene carbons. Vinylic carbon, the word vinylic carbon is they are the alkene carbons, meaning the carbons bearing the double bond of the alkene. They are sp2 hybridized, because if you count the hybridization state of both carbons, they are sp2 hybridized. Now, vinylic carbons sometimes are attached to sp3 carbons. If you look at this carbon here, you see the carbons in red, those are what we call allylic carbons. They are what we call allylic carbons. They are the sp3 carbons, attached to vinylic carbons, meaning attached to the alkene carbons. Vinylic carbons, just know it is the alkene carbons, the sp2 carbons. Allylic carbons are the sp3 carbons adjacent, meaning they are attached. Adjacent means close. They are attached to the vinylic carbons or attached to the alkene carbons. So that's between vinylic carbon and allylic carbon. I've shown you there. It is not rocket science. You can be able to see it. Now, moving on, I think I'm done with explaining what vinylic and allylic carbons are. The next thing I want us to do, I want us to look at, or the last bit of our discussion is I want us to look at the free radical addition of alkenes. Remember, for alkenes, we are talking of addition reaction. For alkane, you remember the free radical reaction of alkane, it was substitution, because you were replacing a hydrogen with a chlorine atom. But for alkenes, we are adding. So alkanes, substitution. Alkenes, addition. So for alkanes, it was referred to as free radical substitution reaction of alkanes. For alkenes and alkynes, it is free radical addition, because you want to add across the double bond and change an alkene to an alkane. Are we together? If you're with me up until that point, please type a 1 for me, and then we proceed. Now, if you have a question, please ask at this point before we start the free radical reactions. Okay, I'm seeing 1, 1, 1. Very good. Now let's proceed. Let us proceed. Okay, thank you. Stop typing. Now concentrate. Stop typing. Now, I'm going to upload an empty blackboard. So let me see, so that we do it together. I'm going to upload an empty blackboard so that we do not copy, we do it together. Now, I hope you have a pen and pencil next to you. If you don't have, pick a pen right now, and my organic chemistry book. Remember, last week we stopped at the alkane reaction, substitution reaction. So today, I want us to do the same, only that you're going to do it for alkenes. All right. So now let's begin. Now, alkenes, for example, I'll pick a simple alkene. I'll pick an alkene, for example, let's pick something like propene. I'll use propene. Do I use propene? Yeah. let me use propene. But I'll give you an assignment with ethene. Can I give you an assignment with ethene? So we'll handle propene, and then for your assignment, I would want you to practice what we do with either a substituted propene or ethene, but you're going to carry out the mechanism for the free radical addition reactions of an alkene. Now, let's see. For alkene, so let me draw my alkene. I'll give you time to draw. We'll move together. So the alkene that I want us to use is, let's use a 2-methyl propene molecule. So 2-methyl. So for example, now here, let's have 2-methyl. Let me draw my 2-methyl propene, CH3. And then CH, we've said 2-methyl. So at position number 2, we have a methyl. And then, sorry, we can't have a methyl and have a hydrogen at the same time, because this is an alkene. That carbon will have more bonds. So that carbon is doubly bonded to a CH2. That is your 2-methyl propene molecule. Now, this molecule, for it to, the heading of your topic is free radical addition reactions of alkenes. Name it that. Free radical addition reactions of alkenes. And then we put this. It is reacting with, let's use HCl, hydrogen chloride, liquid, not a gas. In aqueous state, it's a gas, but it's diluted in water. And then this reaction takes place in presence of peroxide. So in presence of a peroxide, we can use hydrogen peroxide or H2O2. H2O2. Somebody is saying my writing is not visible. The rest of you, are you seeing my handwriting? You need to see that blackboard. Are you able to see that blackboard? So a few people are telling me no, 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 no. Okay. Somebody is saying yes. Some of you who are not seeing, well, what kind of phones are you having? There are few people who are saying yes. So those of you who cannot be able to see, nyi mko na simu bonoko. Some of your phones are questionable and I can't help you. You need to see that blackboard. So find a friend who has a phone that is visible. I told you to sit with your friends. See, my class, it is at LBB. I don't mind if some of you go to that class and use it, or assemble somewhere. So find somebody who has a phone that is visible. Now, because quite a lot of you are seeing. The ones who are not seeing, they are very few. Nyi mko na simu bonoko. Simu mbaya mbaya. Sasa yako na simu mzuri mwenye anaona. You need to see what I'm drawing, because you're going to do the mechanism. The same thing we did last week on the board. We are going to redo it today. But for alkenes, it will be different. For alkenes, it's different from the alkane one. Remember, alkenes, we are using chlorine gas or bromine gas. Here we are using HCl or HBr. Sawa. And then for alkenes, you're only using UV light. For alkenes, we need peroxides. They are the ones that will push the reaction to start. So we need either an organic peroxide or hydrogen peroxide. So that's what you have. I'm sure you've written that. Now, right. I want to dictate the notes from my head. Now, right. Alkenes undergo addition reaction. I can't write it on the board. Those are so many words. So I want to dictate it. Alkenes undergo addition reactions. Alkenes undergo addition reactions. Compared to alkenes, which underwent substitution reaction. And I'm talking of addition reaction in the free radical dimension. Remember, we are dealing with free radicals, compared to alkenes, which undergo substitution reactions. Full stop. For alkenes, free radical reactions require the presence of peroxides. For alkenes, free radical reaction requires the presence of peroxides. E.g., hydrogen peroxide, H2O2, or anorganic peroxide. Organic peroxide, you write it as R2O2. Organic peroxide. You have hydrogen or organic peroxide. Now, the reaction goes through 3 stages, just like the alkane reaction. The reaction goes through 3 stages, just like the alkane reactions. I.e., initiation, propagation, and termination. I.e., initiation, propagation, and termination. Initiation, propagation, and termination. So I want us to write the mechanism for this reaction, and then we come up with the products that are going to form. So write mechanism, mechanism, So mechanism, abbreviate it as MECH. We go on. Now, we've said that it undergoes 3 steps. The very first step, we said it is initiation step. So name it initiation. Now, initiation step. So for alkenes, the first initiation step is the breakdown of the peroxide into radicals. So the peroxide breaks down. So now you write your peroxide to break it down. So now in this particular case, I'll use hydrogen peroxide. The same you can use. So let's break down our hydrogen peroxide. So you will write hydrogen peroxide in a manner to expose the covalent bond between the 2 oxygens. You write it in a manner to expose the covalent bond between the 2 oxygens. And then let's show the, I would suggest, look at what I'm doing. I'll give you time to copy. So when I'm doing it, just look at what I'm doing. Then after I'm done, I'll give you some few minutes to copy what is on the board. So when that covalent bond breaks, and remember we call that homolytic cleavage. When it breaks, an electron goes to each particular atom attached, making that covalent bond. So when you break, I'll show my bonds with red, so that they can easily be seen. Now we form the peroxide radical. Remember, the oxygen is not, sorry, the electron is not on hydrogen but on oxygen, because it was oxygen having that covalent bond. So please know where you're putting that radical of yours. And because there are two, we put a 2 there. So out of what you did last week, this should be very easy. Now, if it was an organic peroxide where I have hydrogen, it would have been an R. Where I have hydrogen here, R. And then where I have hydrogen, R. So same thing. Now copy. Copy. Now, once you formed the peroxide radical, so for alkenes, we have 2 equations for initiation. Alkenes, we only had 1 equation. So for alkenes, we form the radical, peroxide radical. Then the peroxide radical now reacts with your HCl molecule. So equation number 2 of your reaction. Somebody is saying they can still not see. Are we able to see? Can we still continue to see what we have on the board? Let me just close. I'm not logging out. Give me a few minutes. Let me close it and try and see if I can relog in afresh. Let me see if we can log in afresh.
You are currently the only person in this conference.
The one who's rebooted my board. Are you able to see? Is it better now for those of us? So most are saying yes. So I think we are back. Okay, good. Those of you who are not seeing, I believe maybe your phones have an issue, because once I reboot, it should have rebooted the whole blackboard. So it should be visible. If you can't see, please sit next to your friend. I can't help you beyond that. Now, let's move on. Now, like I said, those of you who are not able to see, initially, if you can't see right now, find a friend. Wacha kunisumbua. So now, those of us who can be able to see, I want to assume not everybody, if you are 7 of you, not every phone can be stubborn. I want to assume 2 or 3 will be stubborn. Probability. The other 2 or 3 will be okay. So always sit in class. When we attend class physically, we sit in one room. So sit somewhere closer to your friends. If your phone brings an issue, use your friend's phone. Now, let me proceed. I said initiation. The first step is the peroxide breaks to form peroxide radical. And it breaks the same way we broke the covalent bond homolytically last week. And each atom electron to form the radical. And I said, notice where you're putting your radical. It is on the atom that was attached to the covalent bond, not any other atom, just the specific atom. If I put that electron on hydrogen, nitakuangusha. Why? Because hydrogen was not bearing that covalent bond. The covalent bond between hydrogen and oxygen is still there. It is not broken. So be very careful where you are putting your radicals. Moving, I also said these are two peroxide radicals that are going to form. So know where you're putting that two. It's 2 moles of the peroxide radicals, not molecules or atoms. And then another thing is that I'm saying in the initiation equation for alkenes, there are 2 equations. So we first of all form the radical. Then the radical now breaks the hydrogen chloride. We can either use hydrogen chloride or hydrogen bromide. So for alkanes, we used chlorine and bromine. Here we are using HCl and HBr. Now, we write our radical. Remember, we always begin with radical first. So HO radical. And it is reacting with HBr. Write HBr in a manner that you are exposing what? The covalent bond. Like that. And then go ahead and draw the reaction. So let me just expand my board in a way. Let me do this. Okay, so now something is wrong with it. Let's see if we can bring back what I had drawn. So now I'd said you write your hydrogen peroxide radical, and it is reacting with HCl. So now you show the reaction. I like showing the reaction in red for those of us who are seeing. So I will just pass it down here so that it doesn't interact with the other one. Always when you're drawing, make sure that those arrows of yours don't interact or they don't meet. So now hydrogen peroxide will bring an electron. Hydrogen will also pick the electron. They will form a bond and the other electron will go to chlorine. So you form consequent products. You will have your products as if OH picks a H, you formed H2O. So you formed a water molecule. So when you use hydrogen peroxide, you form a water molecule. When you use organic peroxide, you will form alcohol, ROH. That is an alcohol. But HOH, that is a water molecule. So we form water molecule plus a chlorine radical. Up until there, I believe we are okay. So copy that one. That's equation number 2. Question number 2. This is almost similar to what we did last week. So if you are in class last week, this shouldn't be, it shouldn't be hard. It should just be similar. So those are the 2 initiation equations. So now, once you form the chlorine radical, are you seeing the chlorine radical? Is the one that propels the reaction now. You remember, even in alkanes, we formed either bromine radical or chlorine radical, and it propelled. Now, after you form the chlorine radical, now the reaction goes to propagation step. Let's go to propagation step. Let me pick a different page. Now, propagation. Propagation, write it there in your book as propagation. I'll write as prop. Save on time. So propagation. Now, for propagation step, what happens is that the chlorine radical that you have formed, the chlorine radical that you formed in initiation step, equation number 2, it's the one that now conveys the reaction or begins the reaction between itself and the alkene. So now let's write it. So we formed a chlorine radical, Cl radical. So remember, for chlorine, we can put the radical either on top of L or on top of C, because the whole unit Cl is just chlorine. So I'm not, and bromine, we were putting the radical either way, even in between B and R, it's fine because it is just one atom. Now, it reacts with the alkene that we had said, and our alkene was a 2-methyl propene. So we draw our propene and expose the double bond. Always draw your propene and expose the double bond. So CH3, and then C, it is the methyl here, CH3, and the double bond, and lastly CH2. CH2. That's what we have. Okay. So now, I want you to draw this now before we draw the arrows, because there is one thing I want you to focus on. So I give you a minute. Please draw that very fast. And my time is moving. My time is literally moving. We have about 20 minutes to time. So be fast. Within the 20 minutes, I want to have finished. Now, let's now draw how the electrons, the bond is breaking. So now, the first thing, there are 4 questions on propagation. On the handout, I've only given you 2. I want you to write the other 2. Now here in class, I'll teach you the 4. So the first thing is that we can have double bond. One of the double bond, one bond will break. And then one electron will go to a particular carbon. The other electron will pick the other carbon. So when the bond breaks, this is what I'm saying. When this double bond breaks, one electron will go to one carbon. The other carbon will pick the chlorine particle. So now, look at what I'm going to do. I'm going to break this bond homolytically so that one electron goes to that carbon. Sorry. One electron goes to that carbon. That arrow of mine doesn't look nice. Goes to that carbon. Then the other bond, when it breaks, the other electron, meaning the other carbon. Remember, you're breaking a bond between 2 carbons. So one receives an electron, becomes a radical. The other picks chlorine. So the other electron, don't cross over anything, picks the electron from chlorine. And from chlorine, I can just do this. It brings its electron. So now let's draw the products. Look at how I'm drawing the products. My product for this reaction is a radical. It is a CH3. I just copy what I have here. And then that CH3 is attached to a C bearing a CH3 atom here. And then that carbon is the one that received an electron. So it becomes a radical. And then I proceed, and now we are no longer having a double bond. One bond has broken. So we have a single bond attached to a CH2, and that CH2 picked a bromine particle. So where the arrow is pointing, that carbon is the radical. The other carbon bearing the double bond will pick whatever radical you started off with. That is the gist. If you understand that, then I'm good. Oh, sorry. It is not BR, it's CL. So sorry. Thank you, Fidel and Owinga. Thank you. I think I've been using BR in my previous class, so my head is configured to BR. So this is CL. Good, thank you. Bromine. It's not bromine, it's chlorine. We started off with chlorine, right? It was chlorine. I was talking of chlorine. The initial, yeah, it is HCl. So it is chlorine. So now let's move on. So my question has disappeared. I'm not going to redraw it. Do I redraw it? That is too much work. It has disappeared. You know, I'm using a page. This is an open blackboard. So sometimes it clears itself. So I said we were beginning with Cl radical. And then this is propagation equation number 1. And it is reacting with our CH3, CH3, double bond, CH2. CH2, not CH3. That one. And then I said the bond breaks in such a manner that an electron goes to that carbon. Doesn't matter where I put my arrows, as long as they are visible. And then the other carbon will pick chlorine. So the other electron, the other carbon picks chlorine. Blackboard today is problematic, but it has accepted finally. So like that, and then we form the products. We form the products there. CH3, that is a 3, even if it is refusing. And then methyl, let me go shortcut, and then it's attached to CH2, and then Cl. Cl, like that. So that's your product. But at this carbon, we had a radical. At that carbon, there is a radical. So write your radical. Write the radical. Now, if you look at that, that is propagation equation 1. That is propagation equation 1. Now, on your propagation equation 1, we have formed a radical. That radical is going to be used. That radical that we formed in a propagation equation 1 is going to be used to react with hydrogen bromide. Remember, whenever you're having this kind of reaction, equation 1 propagation forms a radical. Then equation number 2 of propagation reacts either with the molecule. So now know the difference. That equation number 1 will react with the product. So
You are currently the only person in this conference.
equation number 2 will be able to now react with the molecule of choice. Somebody was saying they're not seeing my blackboard. I've tried to refresh my browser. I want to assume that my blackboard is seen. Is it visible right now? I've refreshed it. I hope it's visible because I need you to see everything that I'm doing. Now, I want to assume yes or no, visible. Yes, some of you will sit down in groups and discuss with others because there are some who you are continuously saying you can't see my blackboard. Most of you, you can see my blackboard. Okay, let's continue. Those who can't see my blackboard, discuss with your friends after my class, not now. So now, The radical we formed in equation number 1, let's move on. Radical we formed in equation number 1 becomes our reactant in equation number 2. So write it CH3 and then C, and then that C had a methyl and it was a radical, and it is attached CH. I'm just copying that radical. So I'm hoping you've copied with your pen and pencil. It's easy. CHCl, that's what we have. So I've just copied that structure here. So it reacts with HBr. It reacts with the molecule now, HBr. Sorry, HCl we are dealing here. So HCl opened to show the reaction. Now let me pick my red pen so that we see it clearly. So this brings the electron and this bond breaks. The electron from hydrogen goes that direction. The electron for chlorine goes back to chlorine. Draw the structure. You can draw the structure out of this. The structure that comes out of it is basically you have CH3 and then C. There is a methyl there, or we can put it in brackets. And then we have a hydrogen that has added. And then lastly, we have CH2Cl. That's the first compound that we have. The second compound is a chlorine radical. If you're together till that point with me, please type a 1 for me. Type a 1. If you have a question, ask now. Good. I believe this should be easy. After what we did last week, this should be quite easy. It's only different, but it's easy. So I'm seeing a few ones. Those of us who are not seeing my board, there is a Sylvia somewhere, there is a Karen somewhere, Oscar, Richard, Favor, Caroline, Susan, Justus, a Benson, Brian, those guys, Richard, who've understood what I'm saying. Then you guys can go and find out. Edgar, you are becoming too much in my class. You're telling me you're going crazy. What do you want me to do? I'm not a mental health lecturer. I'm an organic chemistry lecturer. So if you're going crazy, what does that have to do with organic chemistry? If you have nothing to type in my class, please log out. It's not a must for you to be in class. Don't make my hormones start going ballistic. You are all grown ups. If you don't feel to be in this class, toka haraka haraka, tuja kulazimisha. Otherwise, if you're communicating here, communicate things to do with organic chemistry. If it is nothing to do with organic chemistry, wait and communicate it to the correct person. So either go to hospital or go and see a guidance and counseling teacher who can help you with your raising it. Otherwise, if you do this again, I'll chuck you out of my class. And if I remove you from class, you'll not be able to log in. So don't dare me. Now, besides a few rotten eggs like Edgar here, the rest of you, I want to believe you are at par with me. But please, do not sleep today if you've not understood what we've done. Make sure you meet somebody who's understood, sit down and discuss this. Now, this is the first two propagation equations. I say I want to give you propagation equations. Now, the other two, I know we are pressed for time, but we will finish in time. Bear with me. The other two equations. Now, look at it. Look at this molecule. You see, in the first breakage, remember the double bond is between carbon 1 and carbon 2. If we were numbering this molecule will be carbon 1, carbon 2, carbon 3. So remember, the double bond is between carbon 1 and carbon 2 of propene. But when we wrote the mechanism, in the first mechanism, the radical went to carbon number 2. We want to write another mechanism where the radical now goes to carbon 1. I'll repeat that point. The double bond is between carbon 1 and 2. So for the first product, we wrote the product where the radical went to position number 2, carbon number 2. What if the radical breaks to go the other way? Because what, okay, this is the most, you'll form two products there. You will form 1-chloro, this product is a 1-chloro, 2-methyl propene. But now we're going to form another product. It forms mixtures of products. So now we want to write mechanism for the other equation where the radical goes now to carbon number 1. So now let's do it. So we'll have 4 propagation equation. On the handout, I've given you 2. I want you to write the other 2 for me. But now here in class, we're going to do 4 of them together. So now let's redraw. So we are beginning propagation equation 1 for product number 2. This was product number 1. Now, propagation equation for product number 2, let me go to slide number 5. Number 5, now let's rewrite exactly what we've written. We'll go exactly what we've written, but we'll change the direction of our arrow. So it is a chlorine. We started with radical. So write your chlorine radical. It was reacting with your alkene, and our alkene was a methyl, 2-methyl. So CH3, and then C, that C had a methyl here, and it is doubly bonded to CH2. CH2. So now, look at the board. I'll give you time to draw. Look at the board first. So initially we drew the arrow coming to the middle carbon, and that's the major product. But now, what if we broke that covalent bond and the radical went to carbon number 1 here? So that's what we're gonna do it the second time round. So the radical goes to that carbon, and then the other brings, and chlorine brings its own electron there, and we draw our products. We draw our products. So our product is, if the radical went to the last carbon, then it means then the middle carbon is the one now attached to our chlorine particle. So we have CH3, C, methyl, and then this carbon is attached to chlorine came here, Cl. Sorry, let me write it well. Cl, and then that carbon is attached to CH2. CH2, the 2 is refusing until it accepts. And then remember that carbon is going to be a radical because it received the electron. So when I'm there, am I there with everybody? Are we together? Up until this point, are we together? If you're together with me, please type a 2 as we move on. Type a 2. Okay, good. Sylvia says, yes, we are together. So I'm just doing the converse of what we did the first time. Now, okay, good. Now, let's continue. Once that radical has formed, remember I've not put a methyl here. Put it for yourself. Now, once we form this radical in equation 1, you react that radical with the molecule, which was the HCl molecule. So react it with the molecule. We have CH3. So we have CH3, CH3, and then it's attached to a methyl, a carbon bearing a methyl. So carbon. And my board is refusing. it bears the methyl. So I'm just copying what is there. We had a chlorine here, chlorine there, and then we have our CH2. Awi, nilete charger hii laptop. So we have our CH2. Could be that my phone is my laptop is misbehaving. Could be low charge, but anyway, we shall continue. So now it reacts with HCl, the molecule. And then you do the very thing that we've been doing initially. So it picks, the CH2 picks the hydrogen and we form a chlorine radical out of it. So now that is the next step. So let me pick my red pen and we show the movement of electrons. Very easy. So electrons move in this manner. It picks the proton and then the other electron goes to chlorine. Remember to those arrows as curved as possible. Remember they are curved arrows, and then single-headed arrows. So now we write the product. The product of our reaction here is we have a methyl. We have a methyl. Let me draw it to make my work easier. We have a methyl, and this carbon has a chlorine atom attached and a methyl group attached. So I'll label this as chlorine, Cl. I want to draw stick diagrams, make my work easier. Cl attached there. And then at this point, I have CH3. So that's the molecule that I'm having. CH3, and then C, it has a methyl, CH3, and chlorine at that point. So this is the molecule that I've drawn here. I've just drawn stick diagram. If you can't see it in stick diagram, please draw indicating the molecules, the atoms for yourself. So I have that plus a Cl radical there. So that is propagation equation number 2. If you can't see, I've said if you can't see the stick diagram, please write CH3, then CH3 up here. There was a CH3 here. And then Cl and CH2. And the CH2 picks a proton, so it becomes CH3. So it's CH3, and then C, it contains a methyl group and a chloride group, that middle carbon, and lastly CH3. So that molecule is a 2-chloro, 2-methyl propane molecule. That's what I've drawn. 2-chloro, 2-methyl propane. Propane, carbon 1, carbon 2, carbon 3. That's exactly what you have. Now, if you're together up until that point with me, please type a 3. We want to now conclude. I have like about 10 minutes to conclude. We want to conclude. I've seen the first 3 from Amy, Samuel, Sylvia, Timothy, Bravin, Richard, and so on. So those 3 are enough. Let's continue. I believe there are few who are with me. We continue with those ones who are with me. If you haven't gotten what you've said, please ensure you don't go to bed today without getting it. Now, the last stage. So there are 2 products for this reaction. We either get a 2-chloro, 2-methyl propane molecule out of addition reaction of alkene with hydrogen peroxide and hydrochloric, hydrogen chloride gas or liquid. Or we get a 1-chloro, 2-methyl. So you notice we have 2-chloro, 2-methyl, or 1-chloro, 2-methyl. Those are the 2 products. One product is a major product, the other one is a minor product. I'll not tell you which one is major, which one is minor. You're too young to know that. So I'll leave that. Once you know the reaction, that's okay with you. But there is a major product and a minor product. So it's a mixture of product. Then we go to the last stage. The last stage is now the termination stage. Termination stage. Now, for termination stage, look at the radicals that you've created. You started off creating a peroxide radical. Remove it. So termination, you remember, we combined radicals to remove them as molecules. So remove your peroxide radical. So that was RO radical. Sorry, that is wrongly written. The radical is on top of oxygen plus RO radical. Terminate it to form. Sorry, we began with hydrogen peroxide. So for your cases, HO, not RO. So write HO plus H. If we were using an organic peroxide, it would have been RO. So you terminate it to form what? Hydrogen peroxide, H2O2. Or you can simply write HOOH. Same thing. Now, it's been terminated. The second radical that you formed was a chlorine radical. Terminate it with itself because you're using HCl. So terminate chlorine radical with itself because we form numerous chlorine radicals in different stages. So terminate it with itself to form the chlorine molecule. And then the other radical that we can form is we have RO and we have chlorine in first step. You can terminate them together. We have RO or HO plus chlorine radical, terminate it to form the hypochlorite acid, the chloric 1 acid, HOCl, hypochlorous acid. I think that's what you are calling it, or chloric 1 acid. So now, the bleaching agent, because this is the bleaching agent. When you use JIC, JIC has this. It's the bleaching agent. Now, you terminate those ones. Now, you go back to the other radicals that you formed. You remember the radical you formed, the radical in the being with the carbon in the middle. So let's go to the other molecules that you formed. You formed this molecule, CH3, and it had C, a methyl, and the radical was in the middle. That was the first propagation equation, the first product that you formed. And you formed this radical, CH2Cl. That's what you formed. So terminate this with Cl so that you form the dichloro product with Cl radical. And then terminate this molecule with itself. So when it joins to itself, draw the molecule that comes out of it. And then the other radical that you formed was CH3C methyl Cl, and then the last carbon was now the radical, CH2 radical. So you had that. So you have this radical and that radical. So terminate this radical together with chlorine and get the product, get the product. And then the second step also, another termination, get the same radical, terminate it with itself. You remember how we were terminating a methyl radical with itself? Methyl radical gave you methane. But now in this particular case, you're not going to count all those carbons. When you terminate it with itself, so for example, this guy together with itself, this guy, I will write here ×2. If you terminate these two with the cells, don't write for me ×2. Draw that radical, draw another radical, and then you give me the products here. So when you terminate it with itself, when the two attach, writing it is just simple. See, people make organic chemistry tough. It's not tough. So you write CH3 and then attached to a carbon, and then this carbon has a methyl group, CH3, and then this molecule had CH2Cl. Now, if you terminate it with itself, I'll show a bond with black. That's the new bond that you are creating, because the radical for the first molecule, an electron from the first and an electron from the other molecule, gives you the covalent bond, this covalent bond. Now, that covalent bond, you redraw the same molecule because you're terminating the molecule with itself. So redraw the same molecule. It is attached to a C. That C is attached to a methyl. That methyl was attached to, that C was attached to a methyl here. And then it's attached to CH2Cl. That is when I've terminated radical A with itself. I've gotten the product that I've drawn in red there, and the new covalent bond, I've drawn it in black. Now tell me, can't you terminate radical B with itself and draw the molecule for me? The answer is you can. Because now you just form another bond between, now it is more or less, in fact, that is the easiest to write. You'll have CH2 and then it's attached here, a bond here, you have another CH2 and redraw the same molecule backward. So if you're together up until this time, we are on termination. So I've left your assignment to be terminate A with itself. You give the products. Terminate B with chlorine and then terminate with itself and write the product. So I've written for you the product where A is terminated with itself. Now draw the product where B is terminating with itself to form that complex structure. So now, if you're with me up until this point, please type a 4. If you have a question, ask. Favor, Collins, Brighton, Samuel, Timothy, and a few others, Osters, and so many others, you're together. So for your assignment, check out the handout, and I've given you 2 propagation equations. Please add the other 2 propagation equations. And then on termination, write all the termination equations, because add 2 more propagation equations and then include those in your termination and write all the equations for termination. They are there, but they are not all of them. I just kick-started for you.